Welcome to part 3 of our notes on earthquakes. Now, some of you might be wondering, how do we get 3 parts of just one topic on earthquakes? Well, I'm trying to keep these videos shorter in length. I could do it all in one video, but the video would probably be 60 minutes long. And which makes sense, because typically when I present these notes in class, they typically take a full class period and part of a second class period. But what I'm trying to do is break the notes down, so if I assign these at home, you don't have to take notes for more than 20 minutes at a time. So this is going to be part 3, and this should be the final installment, or it better be the final installment on our earthquake notes. Now, we left off by talking about earthquakes. We looked at lots of different damages that was the result. So right now we're going to take a look at the written notes. So what are the results of earthquakes? First of all, you're going to get damage to structures. Freeways, bridges, buildings, homes, water, gas lines, electrical lines. These are all going to be damaged because of earthquakes. You're going to have your social and community challenges. There's going to be lack of food, water, shelter, job losses, higher prices because everybody needs everything. It's the law of supply and demand. So you might look at these, the results of the earthquakes are going to create all these things, challenges, this lack of food. It's a lot like Hurricane Katrina. So natural disasters in general are going to cause these same problems. And earthquakes are no different. However, you have something unique with an earthquakes. Earthquakes can, and not all earthquakes cause these, but some earthquakes can actually create something called a tsunami. And these are huge waves. And as a result, when they come up, these huge waves come on the land, they're going to cause mass flooding and possible death. So what happens with the tsunami? Okay. Now I just started this notes, but unfortunately I didn't set my pen. So what I got to do is I got to change the ink color to red. And so now I have it. So what happens with an earthquake is when you have some faulting going on, notice how this block of land pushed up. And it's not just a little chunk of land. This piece of land might be, half the size of a state, or it might be 30, 40 miles long, and maybe 150 miles this way. So it's going to be a large piece of land, and that large piece of land, when it's thrust upwards, and it might move 3, 4, 5 meters, it's going to push the water up. Now, what's the water going to do? You can see over here, once the water comes down, it's going to move into all directions. And this is what creates your tsunamis. So not all earthquakes create tsunamis. One, they have to be around water. And secondly, you have to have this type of upward movement. If it's a strike-slip fault where you're just sliding past each other, you're not going to have this type of vertical movement, so you're not going to have your tsunamis. Now, tsunamis can reach 30 meters high. So you're looking at a tsunami wave would be taller than this school that we're sitting in. And these waves can actually travel as fast as a commercial airliner. And we're talking about 500 miles an hour. Now, are they all going to move that fast? No, but they could move that fast. And the other thing that we know is they're going to travel long distances. It could travel halfway around our planet. So what happens with a tsunami? Now, if you were out in the middle of the ocean and a tsunami wave came by, if you were on your boat, you would rise up and you would come down, and you would barely notice it. If you had a buoy, it can notice it. But if you were on a ship and you get this up and down motion anyway, you're not going to feel much. However, once the land starts to come upward, and this is going to happen on your continental shelf, and as you move in, the water is going to be less and less deep. As you start to move in, now all of a sudden this wave is being pushed up, and pushed up even higher, and pushed up even higher. And one of the interesting things that typically happens with this, if you were on the beach here, say this was me, here I am. Let me give myself some eyes so I can see, and I'll smile. Oops, sorry, that's not much of a smile. The pen slipped. But maybe I should be frowning, because if I was on the beach and I noticed that the water used to come up to this area, but now all of a sudden the water has, oops, sorry, pushed the wrong button. If I noticed the water left and all of a sudden what used to be water was now beach, I'd get worried and I'd actually start running the other way. Maybe climb these trees to get tall enough. Because if that ever happens to you, we know that a tsunami is coming. And it's kind of interesting. A lot of times when tsunamis happen out in the Pacific Ocean, a lot of the islanders, people that live there, they know what's happening, and they'll actually run, they'll take cover. But a lot of times, a lot of the tourists that are there are just gawking at this, wondering, wow, what's happening? This is really neat, not knowing that this wave is headed towards them. Let's see if this animation works. Now, this animation is working. Remember a few years ago in Indonesia, an earthquake happened, and this just shows the wave, the tsunami that came around. So even if you look in the back side here of Sri Lanka, that wave makes it there. So even though the earthquake happened right in this area, the wave went quite a ways. Here's another one. And look at the back side of Sri Lanka. You can see, even if you were on the backside thinking, oh, the rest of the island's going to protect me, no. The water actually goes right around. And so when it looks down here, approximately 229,000 people died. Most of these people did not die because of the earthquake itself. And it was a larger earthquake. Most of the people died as a result of the tsunami. And it's kind of depressing. You hear about children being ripped out of their mom's arms as their mom was holding them, trying to outraise the tsunami and trying to stay afloat. And unfortunately, when a tsunami happens, a lot of the people that die are the young, who can't swim, who can't fend for themselves, or the elderly, who are too weak to swim through this or to climb up a tree to survive. And so you can see, this is what this one area looked like before, and now you can see what it looked like after. So I mean, you're looking at complete destruction. So, what are seismic waves? Seismic waves are the waves of energy caused by the sudden breaking of the rock within the earth or an explosion. And they are the energy that travels through the earth and is recorded on seismographs. So the breaking of rocks can create earthquakes, but humans can create earthquakes themselves. Just let off an explosion, and you're going to get seismic waves. Quarries often create seismic waves. Now, are earthquakes always caused by faulting? Well, no. Sometimes earthquakes are created by volcanoes. It could be lava coming into a new magma chamber. It could be gases moving through and the rock shifting within a volcano. So not just earthquakes or plates sliding past each other are not the only cause of earthquakes. The earthquakes could be caused by other things as well, such as a detonation of a nuclear bomb. And all these tests that were done in the 70s, 60s were recorded. Oh, let me push. There we go. So there are different types of seismic waves, and there's two main types we're going to talk about. One being a body wave, the other being a surface wave. Body waves travel through the body of the earth, so they travel through the inner layers of the earth. Surface waves actually travel on the surface of our planet. So we're going to take a look at these waves. So when we look at seismic waves, here's some cool animations. So we're going to look at some more animations as we move through. So the first type of body wave is called a primary wave. Sometimes this is called, shorthand, is just a P wave. And the reason why it's called a P wave is because it's a pressure wave. These are the fastest waves. They can penetrate both rocks and liquids. So the rocks being a solid, they can penetrate both solids and liquids. Now, how far faster they travel? This little sign means approximately. And they travel approximately 5 miles per second. So think about that. If an earthquake happened in Reedsburg, we'd feel that within 10-15 seconds. And the reason why they call it pressure waves is because it's like a slinky, where you look at the slinky and it's just going back and forth, back and forth. So this one pushes this wave, this pushes the next one, this pushes the next one. So if you took a slinky and held it like this and just moved it back and forth, this is how these waves would feel, or this is how they would look. Now, if you were on the other end of one of these waves, if you feel a sudden jolt, that is your P wave that first came in. So here's another one. Look at this black box right here. It's kind of neat how this works. See how it's pushed and it comes back? It's going to go through again. So just watch it as it comes through. Watch how it pushes and then it comes back. That's how a P wave travels. Now, the second type of body wave that travels through the body of the Earth is called the secondary wave. Why is it called the secondary wave? Because it travels second. Remember, the P wave is the fastest. It could travel about 5 meters per second, or miles per second. So let's back up for a second. Let's double check this. So here is 5 miles per second. So it's not meters per second. It actually travels faster than that. So here it travels approximately 2 miles per second. And when we look at this, it's slower than the P wave. So they call it the secondary wave because it comes in second. Sometimes it's also called a shear wave, which is another reason why they call it the S wave. And this is the interesting thing about secondary waves. It cannot travel through liquids. This is huge. This is why we know part of the inner Earth is liquid, because depending on where an earthquake happened, we do not get any secondary waves. So when we look down below, this is how it would happen. If we took a rope and we just toss it like this, this is how the S wave would travel. So watch it up here. Basically, it's like a slinky where they slap this up, and then it just goes up through the whole thing. Let's watch it once more. Watch the black box. So you can see how it's going to go up and it's going to come back down. Now there's a couple different types of waves. There's body waves and surface waves. Surface waves travel on the surface of the Earth. And one type of surface wave is called the love wave. You might say, why is it called the love wave? It's named after a scientist or a seismologist who studied waves. So they call it the love wave. Sometimes for shorthand they just call it the L wave. And this is the fastest surface wave. Now this is kind of interesting. Look at it here. It actually goes back and forth. So you actually see it best when it first starts. Here it looks like it's just going out, but it's basically going back and forth. So you can see the motion right here as we look at it. Now the other type of surface wave is called the Rayleigh wave. Most of the shaking felt from an earthquake is due to the Rayleigh wave, or the R wave, which can travel, can be much larger than the other waves and can travel at 1.9 miles per second. So it's a little bit slower, so it's not going to get there quite as fast as, I'm not sure why that turned up. It's not going to travel quite as fast as the secondary wave. Now, when we talk about the surface waves, they basically travel together. They're in conjunction. So they're both going to cause a lot of damage. And people will disagree. Some people say a lot of the shaking is caused because of the earth waves. Some people say the love wave, as ironic as it is, the love wave actually causes the most damage. But basically the R wave, the Rayleigh wave, and the L wave, the love wave, are going to work together, and they're also going to cause a lot of damage. Now this motion is interesting too. It's kind of a lot like an ocean, where it's going to be undulating. Now look at this one. You might say, well, how is this different than the S wave? Well, it's got this circular motion right here. At the S wave, this just went up and went down, but this one actually kind of goes around in a little circle. So it actually has a different path than the S wave. This is kind of neat. So if you just watch one, you can see how it moves around in a circle. So where an earthquake actually happens, where it actually happens is called the focus. Now, if we would go directly above the focus, where it happens on land or on the surface of the earth, that's actually called the epicenter. So here's where the earthquake actually happened. Now, most earthquakes typically happen within 100 kilometers or so of the surface of the earth. Although you can have earthquakes happening as deep as 700 kilometers down. 700 kilometers is approximately 430 miles or so. So when we look at a seismograph, normal background noise, your first wave, this would be your jolt. This is going to be your P wave. Then you might have a few seconds where it's not shaking that much, and all of a sudden now your S wave comes in, followed quickly behind by the love wave and the Rayleigh wave. So do you remember when we talked about the layers of the earth and how we were able to figure out the layers of the earth and what they were? Well, what I explained was earthquake waves. These seismic waves, they travel through the earth, and they will refract or they will bend So they may be bend or they may reflect. So if they bend and reflect, they will come off this way. Or they may hit a layer of the Earth and they may refract, where they just shift a little bit. And this is how scientists are able to figure out where the different layers start. Now, first of all, we have a shadow zone. This slide is entitled Shadow Zone. And the reason for that is, remember, S waves cannot travel through liquids. So you have your S waves traveling through here, and then they get to this outer layer of the Earth called the outer core, which is liquid. But when it gets to it, it stops. It can't travel through it. So here on this entire side of the planet, you will never get S waves if the earthquake happened on the other side. Now there's also, because these things are reflected or refracted, there's also a shadow zone where you're going to get no earthquake waves whatsoever. No S waves, because it can't travel through the liquid, and because of the way these things are bending, these P waves are bending, you're not going to get the P waves as well. And that's called a shadow zone. So again, I briefly mentioned before, the focus is the origin of the earthquake. If you remember in math, when we looked at a graph, 0, 0, coordinates 0, 0 is called the origin, and that's because it's the center of the graph. It's where everything else originates. Same thing here. The focus is the origin of the earthquake. It's where it actually happens. Now the epicenter is the point directly above the focus on the surface of the Earth. So here's your focus, and your epicenter is directly above it right here. Now this does conclude the notes, and as always, if you have any questions or concerns about anything with earthquakes, please stop and ask your science teacher. Your science teacher, especially me, would love to sit down and talk about earthquakes, because I really like geology. Geology rocks. You get it? Ha. So, goodbye, and again, ask questions if you have them.